This is Shijie from Lund University. The topic I'm going to talk is a novel approach for reaction progress variable generation. It's divided into 4 parts. Firstly, research background. The Flamelet-based combustion model are widely used for combustion simulation, which is computationally cheap as compared with detailed chemistry-based models. Let's take the flame generation manifold, or named as FGM, as an example. It has 3 steps. In the first step, a pre-processed procedure is introduced by solving one-dimensional canonical flame, such as counterflow non-premixed or premixed flames. In the second step, the flame temperature, species mass fraction, and other properties from the one-dimensional flame are tabulated using a mixture fraction and a progress variable. We call it as laminar or turbulence Flamelet libraries. In the third step, the mixture fraction, progress variable, and their variance are transported in the computational fluid dynamics. The temperature, species, mass fraction, heat capacity, viscosity, and other chemical properties are obtained from the Flamelet library. This is a mature method which has been widely used in many applications such as premixed flame, non-premixed flame, and partially premixed flame. However, the definition of progress variable in the second step is not well defined. We will focus on this progress variable and find a way to automatically generate reaction progress variable. Actually, it has an agreement for evaluating a good progress variable, denoted as YC or normalized to be C. First, the transport equation of the progress variable should be easy. We don't want to introduce more model assumptions or closure for the transport equation of progress variable. Second, the reactive scalars, such as species mass fraction and temperature, should not change too quick or too slow. It's better to have a comparable time scale with the progress variable. Third, and the most important thing is that the progress variable should have 1-to-1 correspondence to the thermochemical state. This is also the reason why we call it a variable indicating progress of the chemical states. It gives a failure. I will give a failure demonstration later to show if we don't have 1-to-1 point correspondence, what should we get? From the literature review, we found that there are many progress variable definitions, which sometimes is ad hoc. And most of the progress variable definitions are based on the hydrocarbon field. It involves carbon oxide and carbon monoxide, CO2 and CO. However, in terms of carbon-free fuel, the progress variable definition is not clear yet. For example, ammonia is an important carbon-free fuel which has no carbon oxide and carbon monoxide in the products. Therefore, it's desirable to have an automatic progress variable approach to generate progress variable for this carbon-free fuel. In this section, we will show a novel method which can generate suitable progress variable definition. The progress variable is in general defined as linear combination of species mass fraction. So its transport equation is similar to species mass fraction transportation. The first principle is met. Equation 1 shows the general form where Wi is weighted coefficients. YC is a non-normalized progress variable. Yi is the species mass fraction. NS is number of species. Lambda is a flamelet parameter. In a premixed flame, lambda could be defined as distance from the flame surface. In an unsteady non-premixed flame, alpha could be defined as physical time. To meet principle 2 and 3, we require that YC increase monotonically from fresh to burn gas. And we also require that any species mass fraction should not vary too rapidly versus YC. This gives two sets of constraints shown in equation 2. We can tune the parameter alpha to adjust how quick can the species mass fraction varies versus YC. Those constraints could be simplified as equation 3 or equation 4 like this. In equation 4, for given alpha, the vector x and the scalar b are determined. They can be solved analytically as linear programming. Each equation stands for a line. Plenty of lines resulting in a feasible region show the orange triangle on the left figure. However, there are many equations. I stands for species, J stands for Flamelet parameter, K stands for mixed fraction in non-premixed flame and equivalence ratio in premixed flame. The total number of constraints has an order of ns times nl, n lambda times nz, which are too many. For example, a methane air counterflow flame library is total number of 0.29 million constraints equations like equation 4. It's computationally expensive to solve it using linear programming. Here, we found a new way. We introduced the artificial neural network to solve it as a classification problem. See on the right-hand side. The constraint equations was converted to be equation 5. Now we locate all of the coefficients into a ns dimensional space. Each constraint corresponds to a point, denoted as green or white in the right-hand side figure. Find a good weight coefficient W means that we can find a hyperplane. This is a plane in 3D and a line in 2D, which can separate the blue and white points. The points are used as training data, so we don't worry about the number of constraints anymore. In contrast, the more, the better. The more constraints, the better training precision will be obtained. After determining the training point, we also need a loss function to evaluate the training precision. And sometimes the constraint leads to plenty of feasible solutions. We need to sift the optimal results. So we define a minimization function fw and associated constraint hw. For example, we define fx as the L1 regularization of vector w and h to be sum of wi equal to 1. This will give us a sparsity weight vector w, or we say most of species are zero weighted. This is what we want. The progress variable definition will be easy. On the other hand, the constraint might also result in no solution. For example, we choose an unsuitable alpha, which is too severe for the studied cases. Here we also give a solution. We use a soft margin classification technique, which has a Lagrangian function like this. Well, Xi is slack variable allowing some errors. Beta is a penalty constant. A large beta enables severe penalty for violating the constraint and vice versa. After getting this method, we try to validate the new method. We studied a set of one-dimensional premixed flame. The initial condition is 600 Kelvin and atmospheric pressure. Fuel is a mixture of ammonia, hydrogen, and nitrogen, according to literature 4. We have 3 cases A, B, and C with the equivalence ratio of 0.8 unity and 0.1, 0.2. We use Cantara to solve the one-dimensional flame and get some of chemical properties, and we use current ANN method to generate a progress variable weight coefficient W. The final part shows some results. First, we got an optimized progress variable, which has 12 non-zero weight shown in table 3. The other species are zero weighted as we use L1 regularization. The bottom left figure shows the species mass fraction before tabulation. The horizontal x normalized is a normalized flame parameter, which can be understood as physics distance x. You can see that NO, NO2 are plotted. We will try to use this 2 mass fraction as progress variable to replicate OH, the circle, blue circle. We also have an optimized progress variable, the blue line. The bottom right figures show OH mass fraction predicted by progress variable of NO, the red line, NO2, the black line, and the optimized progress variable. It's seen that the red dashed line is veiled, which means that if we use NO2 as progress variable, it's not possible to predict OH because one progress variable corresponds to more than one OH mass fraction, which violates principle 1, principle 3. If we use NO as progress variable, see the red line, it decreases rapidly near 1, this place. This is because that NO almost does not increase after a specific time, this place. So this quick change violates principle 2. A good progress variable should increase monotonically and smoothly. NO and NO2 are not good candidates. We cannot copy the experience from hydrocarbon fuel progress variable definition. This 6th figure shows the mass fraction of the fuel, important intermediate species, and main products of the ammonia-hydrogen combustion. Ammonia generation generates NH and finally produces nitrogen. Hydrogen generates OH and finally produces water vapor. All of the equivalence ratios are plotted, including fueling, stoichiometric mixture, and fuel-rich conditions. It seems that in all conditions, the species mass fraction has a 1-to-1 correspondence to the optimal progress variable. It also evolves smoothly, which means that the current progress variable is good. In the present work, a novel approach for automatic generation of the reaction progress variable is proposed. The artificial neural network is adopted to solve the constraints and provide optimal weighted coefficients. Specifically, we use L1 regularization to encourage zero-weighted species. We convert constraints to be classification point to train the artificial neural network to find a hyperplane which solves a large number of constraint equation problems. We introduce slack variable to let the classification to be a soft margin classification problem, which allows some error when the constraints are too strict to yield feasible solution. Finally, we use this approach to study a set of one-dimensional ammonia hydrogen L premixed flame and give an optimal progress variable. Thank you for your attention. If you have any question, please send email to this one.